रामलाल छोले लाओ।
आया सर।
रामलाल छोले लाओ। छोले लाओ। छोले लाओ। छोले लाओ। छोले लाओ। छोले लाओ।
Shreya Kumari, nice to see you back. Hi Srinu, hi Tejaswini, hello Reshma. Good morning, my lovely warriors. So, those of you who want to get in touch with me, they were asking, sir, how do I get in touch with you? I want to talk to you. Well, that's my Instagram handle. That's how you get in touch with me. I might take some time, but yes, I will eventually get back to you. So, welcome aboard. Ready to rock today's session, and a big thanks to all of you for hitting the subscribe button, and a lot of thanks for also smashing the like button. And yesterday's session, we have already crossed 1K likes. I'm so thankful, so grateful to all my lovely warriors. So keep this josh high and make sure that you keep spreading this love, keep spreading the channel's name. Make sure you make us proud no matter where you are, because you are a true Vedan who respects all the teachers, who respects all the institutions, and you are right over here to rock today's session because you have faith in us and you want to score full marks, and we won't let that down. All right, so no matter what is your preparation level, this session is just for you. So let's get started, my 12th standard warriors. Yep, Jania, yes, very true. Good morning, Uncharted. Hello, Kushi. All right, welcome aboard. Hi, Shika. Okay, so this will be in English. This entire session will be in English. So let's begin. And what I'm going to do, I'll give you a brief overview. Chapter, formula. Okay, so what are we going to do? What is the flow of the session? For example, we pick up, let's say, chapter 1. Chapter 1, we are going to revise the formulas first. And once we see the formulas, etc., and then what diagrams or whatever important graphs, all of that, then we are going to go to the application part. In the application part, we are going to see lot of questions. So these questions will be basically MCQs. So lots and lots of MCQs just for you. And then after this is over, then again we'll go to chapter number 2. So that's what is going to happen, and the same process is going to repeat for all the chapters. So this will be a long session, but might not be as long as yesterday's session. Alright, so let's begin the first chapter. You don't have to open NCERT. All I need is your rough sheet. Everybody has the rough sheets? No, this is not going to be a Menti quiz. Everybody has the rough sheets. So I'm expecting around 3 hours, maximum 4 hours. Okay, so that's how it will be. Okay, very good, excellent. So let's begin with our formula revision session, and lots of formulas coming with the application just for all of you so that you rock the term 1 examination. So let's start doing this in the chapter of electric charges and fields. So let's see what are the important formulas and what are the important things that you need to keep in mind. So first let's talk about the charge. So regarding charge, you need to know the properties. Like, first of all, the charge is conserved in isolated system. So basically, if you have one body and if you have another body, this is, let's say, for example, before, and let's say you have another body here, this has a charge of +2, this has a charge of, let's say, I don't know, +7. So maybe they interact with each other. Let's say this gets a charge of +4. Okay, this gets a charge of +4. So then remember, the total charge is 2 + 7, which is 9. So if this is 4, this must be +5. So that's charge conservation. Next thing is basically your quantization. So remember, all the charges are in general integral multiples of E. This is the smallest quanta. This is called as the quanta of charge. N is basically any integer. Okay, and the value of E we all know is 1.6 into 10 to the power minus 19 coulomb. Keep all these things in mind. Okay, perfect. Charge is obviously scalar quantity, unit of charge everybody knows. Great. Then let's go ahead. Apart from this, okay, then how do charges interact with each other? They apply forces, and that electrostatic force is given by Coulomb's law. So Coulomb's law out there, okay, so Coulomb's law, fair enough. And in Coulomb's law, if you have two charges Q1 and Q2 separated by some distance of r, then the force between them, the force of interaction between them is given by 1 by 4 pi epsilon naught Q1 Q2 by r square. Okay, oops, let me just put it properly, Q1 Q2 by r square. This constant over here, this is your Coulomb constant. Okay, Coulomb constant, and that value is 9 into 10 to the power 9. You're supposed to remember it. Epsilon naught is basically your permittivity of vacuum, and the value is 8.85 into 10 to the power minus 12. Now this is scalar form. You should also remember the vector form of the equation. The vector form of the equation will be same thing, 1 upon 4 pi epsilon naught Q1 Q2 divided by r square, but here you can have a r hat. That r hat is the position vector. So for example, this r is the distance. The r vector, if it is like this, if r vector, the position vector of second particle with respect to the first particle, for example, then the force on it will be in the direction of r hat. R hat is nothing but a small unit vector. A small unit vector in this direction. Now you will be like, sir, the force can be this way or that way also. You don't have to worry about it. Q1, Q2 will automatically take care of the signs. You can see, if both the charges are positive or both are negative, the product will be positive. Correct? So this entire term over here will be positive. So the force will be in the direction of R, in the direction of the position vector. If one of them is negative, one of them is positive, then automatically this will become negative. So the force will automatically come to the other side. Everybody got it? All right? Chalo. So if this much is understood, next pointer that you should remember is basically superposition. Superposition, and this is just related to the vector addition of forces. That means if you have multiple charges, let's say 1, 2, 3 and 4, you want to find the force on 3. What you need to do is, due to 1 there will be some force F1, due to 2 there will be some force, let's say F2, due to 4 there will be some force F4. So the vector addition of all of them will give you the net force. So the net force is nothing but the vector addition, F1 bar plus F2 bar plus F3 bar and whatever. Okay, or whatever, sorry, this is F4 bar. Okay, so this is vector addition. That's what something you should keep in mind. Very good, very good. So my god, Divyajot fully binged watched my Pathfinder series. Now your data is off and Wi-Fi is dead. Very good. So please recharge your data packs. You're going to need it a lot because of the marathon sessions. All right, but I'm so glad that you finished your data pack for noble causes. Okay, so if you want, you can take a screenshot of it. It's up to you. But if you're practicing with me, then it's fine. That will be in fact even better. So you can take screenshots once I finish writing this. All right, so I hope you have taken the screenshots. Moving ahead to the next part. But let me also tell you, even if you miss taking the screenshot, you can pause the video even in a live class or even in a recorded class. Not just that, you can also go back even in a live class and catch up at 2x speed if needed. But most likely it will not be. Alright, so Lokesh, like I said, this session will be at least 2-3 hours. Okay, next thing that we are going to talk about is field. Okay, so yes, so let's talk about field over here. Okay, so electric field. Just like two charges have force, a charge Q around it creates a field. So if you are at a distance r, then the electric field at that point is given by, again, 1 by 4 pi epsilon naught, you can call it K, into Q by R square. In vector form, you can write it as E is equal to, again, 1 by 4 pi epsilon naught Q by R square into, again, R hat. What is R hat? R hat is nothing but a unit vector in the direction of the position vector. So this is the position where you want to find the field. Okay, now if you are wondering again, what about the direction? Is field always outwards? No. So if you have a positive charge, then the field is always outwards. But if it is a negative charge, then the field is going to terminate on the negative charge. This is one way of writing field, but there is another way of writing field, and that is via force. So again, if you want to define field, this is how you can define field. So if you have Q and at this point you place something called as a test charge, and the test charge is Q, which is tending to 0. So that means it's a very, very small test charge. Then the field at that point, then the field at any point is generally defined like this: limit Q tends to 0, and this is force by Q. Force by Q. So force acting per unit test charge is called as the field. That's the true definition of field, but this is due to a point charge. So this is field due to a point charge. This is field due to a point charge. Whereas this one, this is in general definition of field. Keep this in mind. Now looking at this, you can quickly understand what should be the unit of field. Force by charge. That means it is Newton per coulomb. Okay, Newton per coulomb is the unit of field. Very good. Yes, we are going to talk about all the terms. Yes, Komal, don't worry. In terms of V, in terms of U, how is it related with V? Yes, we are going to look at all the formulas. Have patience. Yes, we are going to come to that. Yep, we are going to come to that. And yes, there is another unit of field, and that is volt per meter. You will understand why it is volt per meter in a bit. Just hold on for that. Okay, having said that, remember electric field lines. Okay, the density decides whether the field is strong or weak. Here the field is weak, and here the field is basically strong. Not just that, if you have a conductor, then the field lines are always perpendicular to the surface of the conductor, and inside the field is 0. Now, even if this conductor has some cavity, it's okay. Even inside that cavity, the field will be 0 because the charges only reside on the surface of a conductor. In fact, there is a formula for the field on the surface of a conductor. So the electric field just outside, okay, just outside the surface of the conductor is given by sigma by epsilon naught. If you are wondering what that sigma is, this sigma is surface charge density, surface charge per unit area. So surface charge per unit area, it's not divided by 2, it is just sigma by epsilon naught. Keep this in mind. Okay, fair enough. Awesome. I'm just going to reduce the brightness a little bit, probably that will help. See if this works. Is this brightness better? Okay, so that is what surface charge density is. All right, very good, very good, very good. Chalo, let's get moving to the next one. Okay, so you can take a screenshot if you want till this point, and then I'm going to move ahead. Okay, yes. All right. Sir, will the PDF be available in the Telegram group? Well, Priya, let me warn you that the PDF will be available, but only for the problems. Whatever I write on the screen, that won't be available because that gets erased on Google Slides. So when you use Google Slides, there is no such option. Technically, it does not permit us only to, whatever we write, to keep it as it is. Okay, Suhani, I'll come to that. Sigma by 2 epsilon naught कैसे होता है और कैसे याद रखना है. I will tell you about it. Don't worry. Okay, just hold on for a bit. Now, see, once we have talked about field, let me also add some more formulas for field. Okay, see, if you have a charge, and let's say you have some external field, this is some external field, then that charge will experience force. The force experienced by it is charge into the field. Now if the charge is positive, if it is positive, then force is in the direction of the field, but if it is negative, then the force is opposite to the direction of the field. And there are many questions like that. So let's say for example the charge has some mass, then you can find out the acceleration like this, because the force is mass into acceleration and the force is charge into field. So therefore you can get acceleration is equal to charge into field divided by mass. So this helps you for solving problems. Once you get acceleration, you can use kinetics and you can solve the questions. Like S is ut plus half at square, V is u plus at. You can use that because you have just found out the acceleration. Fair enough. Now the next thing that, don't worry, we are going to come to the application part, Harshita, because now I'm just revising the formulas. You'll understand how to use the formulas once we start solving the problems. And meanwhile, I'm also explaining the nitty-gritties and what are the important things that you should keep around that formula while I am showing you all these things. Okay, so pay attention. Okay, now that this is done, all right, the next thing is from field we go to flux. So for example, you have field lines like this and they are cutting through some area. Let's say this is some area through which they are cutting through. That area is basically A, this is the field, then there is some flux associated with it. Now what is flux? Flux is basically flow, and when I say electric flux, it means flow of electric field lines. So the symbol for flux is phi, and because it is electric flux we put a symbol or subscript like E over there, and this is directly proportional to the number of lines, the field lines that cut through an area. So what it means is that imagine if you have an area like this, and let's say for example the field lines pass this way, then if it is moving parallel to the area, is it cutting through the area? No. So in this case the flux cutting through it is zero. The flux cuts through it only when it pierces that area. So if you had field lines which is like this, then the flux is not zero. So if the flux is at an angle and you can split, or rather the field is at an angle and you can split the field into two components, perpendicular and parallel, only the field lines which are cutting through the area contribute in the flux. The field lines which are parallel to the surface, they do not contribute. Hence the definition of flux formula wise is electric field dot area vector. If you are wondering what is that area vector is basically the normal, the perpendicular drawn to the surface. So if you draw perpendicular to the surface, so for example this is a book and I draw a perpendicular, so this is my area vector. Field might be at some other angle. So field can pass through any angle, but area vector is always perpendicular to the surface area. Keep this in mind. But if it is curved, okay, this is for flat surfaces, flat and uniform scenarios. But let's say for example, if it is curved, then you use integration or summation. So it will be E dot dA. When will you use this? This is used for non-uniform. This is used for non-uniform or basically curved surfaces. Meaning your surface itself is curved like this. This is your curved surface. And the field lines, one is here, one is there, one is here. So essentially you divide the surface into small areas. So this is a small area, so this will have a small unit vector dA. The flux through it will be E dot dA. Field at that point into area at that point. Summation is nothing but integration. That will give you the total flux over there. Is that understood, everybody, till this point? Yep. Is that clear, everyone? Very good, very good, very good. Excellent. Cool. Yep. Let's get moving to the next one. Sir, EA cos theta. Well, this is dot product. What is dot product? It is cos. So when you have dot product, if you put in magnitude terms, it will become EA into cos of theta. What is theta? Theta is the angle between them. Theta is the angle between them. Okay, cool. Chalo, let's get moving to the next part quickly. All right. Chalo, let's see some more formulas and then we are almost there for questions. Okay, what is the next part? So if you have a dipole, what is a dipole? So let's talk about dipoles now quickly. So dipoles. So if you have a negative charge and you are separating it by distance L from a positive charge, that is basically a dipole. The dipole moment, this is your dipole moment. The dipole moment is given by the charge. Let's say this is minus q, this is plus q. So you can write it as charge into length. Now in your books it is written as 2L or 2A. Let me tell you, this really doesn't matter. You write 2A or 2L. See, in your books what they have done is, they have assumed this as A, and then they write this formula as Q into 2A. Because obviously L is nothing but 2A. So it's one and the same thing. You don't have to break your head over it. Remember the direction of P is a vector, so it's always from negative to positive, minus to plus, not from plus to minus. Please keep that in mind. Great. Next, the field due to a dipole. The field due to a dipole, minus and plus. Okay. If you are at any distance r and this is theta, then what is the value of field? In general, the value of field at any point is given by, remember this basic formula, Coulomb's constant, dipole moment divided by r cube, and remember 3 cos square theta plus 1. 3 cos square theta plus 1. So if you are on the axis, then theta is 0. Axis means you are on the dipole's length. So theta will be 0. And if you are on the equator, then theta is 90 degrees. So this is a more general formula. Okay. Is that okay? Cool. Chalo. Let's get moving to the next one. Okay, perfect. I'm erasing this now. All right. Then you have torque due to a dipole. So dipole in a field. So when you have dipole in a field, what does it experience? It experiences torque. So imagine you have a positive charge, negative charge, and you place it inside some external field. Let's say this is E, and let's say this angle is theta, and this dipole moment is P. There is a torque acting on it. Okay, there is a torque acting on it. The torque is given by P cross E, which is nothing but PE sine theta. The net force on it is 0. This is only true for uniform field, not otherwise. This is only true for uniform field. Remember, when the field is non-uniform, then the net force may not be 0. The force on this charge and the force on this charge may not cancel out each other. That's something which you should keep in mind. The last thing before we start moving to the problems is Gauss's law. So we have Gauss's law. So in Gauss's law, remember, if you have multiple charges and this is Q1, Q2, Q3, Q4, let's say Q5, and you draw a closed surface, let's say like this, and this is your surface, and there is field over here, etc. Then at every point you calculate what is the flux at that point. So it will be E dot dA. That's the flux at that point on the surface. You add all the flux, that means summation. But for the entire surface, that's why closed surface integral. So this is basically for the entire closed surface. If you add the total flux, what do you get? You will get whatever charge is inside divided by epsilon naught. One more thing, this is only the charges which are inside, like Q2, then you have Q3, and then Q5. But remember one thing over here, this field that you see, this is due to inside as well as outside charges. Both. This is due to inside plus outside charges. Uncharted, I'm coming for field due to different geometries as well. So please take a screenshot quickly. Yep. So Someshwar, this class will be for almost 2-3 hours, bacha. Sir, if E and S are parallel, then flux is 0. So let me tell you one simple thing. See, when the area vector and the field both are parallel, that means the flux will not be 0. The flux will not be 0. In fact, the flux will be there. Area vector itself is perpendicular to the surface. So if field is perpendicular to the surface, flux is not 0. Field, understand there is difference between surface and area vector. Surface means this surface, like the book surface. Area vector is this, perpendicular. So if field is parallel to the area vector or field is perpendicular to the surface, flux is not 0. It's only 0 when field is parallel to the surface or perpendicular to the area vector. Keep that in mind. Yeah, so be careful about that. Okay, now field due to different geometries. Due to different geometries, you should know this. First of all, if you have a charged sheet, then the field goes here also as well as here. So then this field is just given by sigma by 2 epsilon naught. It gets divided into 2. See, how do you remember whether it is by 2 or just sigma by epsilon naught? For a conducting surface, the fields are just outside. What is this? This is just a conductor. In fact, we all know that the field inside is just 0. So it only goes to the one side. So you just write it as sigma by epsilon naught. There is no half-half. Here, in the case of a sheet, which is like a thin sheet, it goes both ways. So half sigma by epsilon naught and half sigma by epsilon naught. That's how you can remember it. Is that clear? Yep. Very good. Now, sir, then when we want to add all the charges, yes, you have to just add all the charges on the RHS. Correct, make it unique. That's all. Yeah, very good. Chalo. Then the next thing that you should remember is due to a wire or a linear charge lambda. Then what is the field? The field which will be radially outward like this. So if you are at some distance r, what is the value of field? The field is, remember it like this, 1 upon 2 pi epsilon naught lambda by r. So this can be also thought of as 2 times of 1 by 4 pi epsilon naught. So whatever Coulomb's constant is there, 2 times of that lambda. What is lambda? If you have forgotten, lambda is nothing but linear charge density. Okay, linear charge density. So it will be basically Coulomb per meter. Then apart from this, which other formula you need to know? Sheet, yes, conductors, linear charge, dipole is also done. Yep, I think that's it. Spheres and shells are not there. Okay, so you can ignore that. All right, cool. Chalo, let's do some questions. Okay, are you ready for some questions? Yeah, sir, if the field is passing through the sheet, you will just add it, Kushal. In fact, there is one question like this. I'll just show you. Okay, so Arjit, for Gauss's law, I'll tell you what. Whenever, see, for example, I'll give you a simple thing. Say, you have a point charge over here. Okay, and you want to find the field due to that charge at this point without using Coulomb's law. You choose a surface, a closed surface. You choose a closed surface like this. Once you choose a closed surface, try to visualize how the field lines will look like. The field lines will look something like this, right? Correct? And at every point, the field will cut through some small area, let's say dA. So what does the statement say? It is E vector dA cos theta is equal to inside charge by epsilon naught. Now what this means is field at every point into area vector into the cosine of the angle between them. We know that the area vector is also in the same direction. So essentially theta is 0 degree. So here basically cos of 0 will become 1. So it will just become E into dA is equal to inside charge. Whatever charge is inside will come on the RHS. Here this field is field due to all the charges that are present. So Q in is just Q and this is just epsilon naught, and because E everywhere on the surface, be it here, here is constant, it will just come outside, and then you just solve the integral which is Q by epsilon naught. So that's how you apply Gauss's law. So Gauss law mein there are two parts, LHS and RHS. RHS mein the numerator has only the charges inside, but this LHS, the field is there for the entire charges, and this integration stands for summation, addition, adding of all the fluxes. A small flux will just be E dot dA. So the total flux will be addition of E dot dA. And what is summation? Summation is nothing but integration. And because our surface is closed, that's why you put that cyclic integral. Is that okay? Cool. Chalo, let's apply the formulas, and here are your questions coming up on your screen. Great. Ready for questions? Perfecto. Welcome Archana, welcome aboard everyone. Three charges 1, 1 and 2 microcoulomb are at the vertices A, B, C of an equilateral triangle of side 10 centimeter. What would be the resultant force at the charge C? That's the question. Come on. All right. Axial and equatorial line, that's what I just told Niveta Paras. I hope that made sense. You can use my general formula, root of 3 cos square theta plus 1. I hope that is okay. All right, Ram, let's do this. Okay, so many of you are saying C, some of you are saying D. Okay, some of you are saying B. I'll tell you a very easy way. So this is 1 microcoulomb. This is also 1 microcoulomb. Let's say this is 2 microcoulomb. This one on the 2 microcoulomb will apply a force like this along this side, correct? It will apply a force along this side. Let's say I call it F1, and this one will also apply a force this way on this side. So this is 2 microcoulomb. Now the vector addition of these two, will be the net force. That's what you need to find. So first start with F1. So what will F1 be? Force due to this charge on this charge, or this charge onto this charge. Why are they two equal? Because 1 on 2, distance is same, so forces will be same in magnitude. So F1 will be just K into Q1 Q2, use this formula, divided by R square. K is 9 into 10 to the power 9. Charges are 1 micro, so 10 to the power minus 6 into 2 micro, so 10 to the power minus 6, divided by distance is 0.1 square. So check this out. So 10 to the power minus 6, 10 to the power minus 6, 2 into 9. Okay, so this is 18. So we have minus 12, and then so it is, I'll just put it over here, 10 to the power 9 minus 12 and then plus 2. All right, so this will be 18 into, so 9 minus 12 minus 3 plus 2, so it will be basically minus 1, so it is 1.8 Newton. Now the net force, how do you find the net force? This is vector addition. See, think about it. This total angle is 60 degree because it is equilateral, and I know this angle and this angle both will be 30 degrees and 30 degrees, correct? Now think, this F1 force will have two components. This red force, the net force, will be the resultant of F1's component along that line. So F1 will have a component F1 cos 30 over here. Similarly, this force over here will also have a component here. This F1 will also have a component there. I hope you can see that. So what are those components which are adding? Those are nothing but the cos 30 components. So just use that. So F1 is, technically speaking, F is nothing but F1's cos 30 component. F1's cos 30 component, okay, plus another F1 is there. That guy's cos component also. So both together you will get the net force. So that's it. So it will be 2 times of F1 into cos of 30. So 2 times of F1. F1 is 1.8. Cos 30 is root 3 by 2. 2 goes. So root 3 is 1.7. Root 3 is almost 1.732. So 1.8 into 1.7, I think it is going to come out somewhere close to 3.12. Just check this out. Just check this out. Is that okay? Yep. K is always 9 into 10 to the power 9. That is Coulomb's constant. This over here is nothing but your Coulomb constant. I just gave it to you. Coulomb constant. Correct? That was your Coulomb constant. Perfect. And How did I find R? It's already given. It's an equilateral triangle of side 10 centimeter. It is given. This is 10 centimeter. 10 centimeter is 0.1 meter. It is already given. That's why I put R as 0.1. Correct? And vector addition law use nahi karenge. Why do you want to waste that time? Yes, you can do that. If you want, you can also find F using your vector addition law. If you want, you can also use, okay, I'll just put it over here. You can also use, if you want, root of f1 square plus f1 square plus 2 f1 f2 cos 60. If you want, use that. You will still get the same answer. It's not going to be the different answer. Is that okay? Cool. Yes. So the field does not matter if the sheet is finite or infinite. It matters uncharted, but we assume that the finite sheet is also so large that we neglect the end effects. Okay, cool. Ayyappan, leave your comments after the session ends. I'll definitely help you out. Is that understood why we do cos components and why we did it that way? If you want, you can also use the vector addition formula which you have learnt in 11th standard. Got it? Perfect. Chalo, let's get moving. So these kind of questions will come for vector addition. Let me tell you, be it field, be it forces, it can come anywhere. So the two important things that you have learned over here is the application of force. You have also learned how to calculate Coulomb's force and also vector addition. Vector addition, that's very important. So option D is correct. Yep, let's get moving to the next one. Yep, Veera, you can definitely crack it because VIT EEE's syllabus is almost similar and the questions are also similar to JEE Mains. So definitely you can. Okay, a force of 2.25 Newton acts on a charge of 15 into 10 to the power minus 4 Coulomb. The intensity of the field at that point is how much? What is the intensity of that field? So Varshad, you have missed the formula revision and you have missed the first question. So join in, you can rewind back later on, whatever you have missed. Alright, Ashika saying A, Gamer saying A. Very good Laiba, very good Prime Guru. Okay, Niveta, let's get going. Hi Dipanchi. Okay, Uncharted also saying C. Santham, Veera, Harita, all saying C. So which formula you want to use? Force is charge into the field. I just told you about it. If you have a charge placed in a field, then there is a force acting on it. So the force is 2.25, charge is 15 into 10 to the power minus 4, field is something which we don't know, so field will be 2.25, I can write it as 225 into 10 to the power minus 2, this guy I can take it below, so it will be 15 into 10 to the power minus 4, 15 will go 15 times, so it will become 15 into 10 to the power 2, so which is 1500 Newton per Coulomb. Perfecto, excelente. Let's move ahead to the next question. This was easy one. Let's get going to the next question. Perfect. You guys are doing fabulous. Very good Kakshi. Very good Kani. Very good Sriniti. Excellente Prime. Very good Srishta. Next question. We have a charge of 10 microcoulomb. It is placed at the center of a hemisphere. Radius 10 centimeter. What is the flux? Only through this hemispherical surface in SI units basically. Okay, come on, let's see how many of you can do this. Come on, my warriors, figure this out. What's the flux only flowing through the hemisphere? I'll help you a little bit. See, this charge is placed here, so the field lines will go somewhat like this. Correct? This is how the field lines will go. I feel out of the total flux that will be coming out of it, only half the flux will be going through the hemisphere. Only half the flux, correct? Why only half the flux? Because if you imagine a complete sphere, so the upper half and the lower half will have the same number of lines cutting through it. So my job has become now simple. So the flux through the hemisphere will be half of the total flux of that particular sphere. Very good. Now, how do you calculate total flux of that sphere? Remember Gauss's law? So this is direct application of Gauss law. So the total flux of any closed object or closed surface is Q by epsilon naught. So it is charge which is inside by epsilon naught. So over here I have just made use of Gauss law. Okay, I've just made use of Gauss's law. Perfect. So the next part will be half into What is the inside charge? It is given to be 10 microcoulomb. So 10 into 10 to the power minus 6 divided by epsilon naught, which is 8.85 into 10 to the power minus 12. So you can do the math. So this will become 10 to the power minus 5, and that will become 10 to the power 10 to the power minus 5, and this will become 10 to the power 12, and you have 2 into 8.85. so check this out. How much does it come out to be? Approximately 10 to the power 7. So I can do one thing. So this is 1 upon 2 into 8.85 into 10 to the power 7. All right, so this 2 8s are 16, so closest number is 20, so 1 by 20 is 0.05, so it will be slightly more than 5. So slightly more than 5 means 6. That's what it will be. C option. Just check this out. Just check this out, because I know 1 by 20 will be 0.05. This will be somewhere like 17, 18 or something like that. So obviously when you have 1 by 20 is 0.05. So 1 by 16 or 17 will be slightly more than this. And 2 decimals gone here. So it will become 10 to the power 5. Make sense? Okay, chalo. Let's get moving. Yes, option C is correct. Perfecto. Moving on to the next question. Yes. So Sai Rama Srinivas, this session will be for 2-3 hours at least. Okay. Let's get going. So the radius does not matter here at all. Yes, Krishna, because no matter how big the radius is, the lines will eventually cut. Either now or then or later. So as soon as it cuts, the flux is counted. So it doesn't matter whether you count it here or there. Makes sense. Yes, Biot-Savart's law will also be covered. A lot of students are saying A. Well, let's see whether you guys are correct or whether you guys are wrong. If this charge is placed here, what you need to do, visualize a bigger cube. And how? Like this. Okay, look at this. I'm just going to draw a bigger cube over here. Just going to draw some more cubes right in front of you. Okay, I hope now you are able to visualize. Yep, like this over here. Okay, perfect. So can you see what I have done? I have added 3 cubes over here. One was the original one, 2, 3, 4. More such 4 cubes below. Okay, more such 4 cubes below. So it will look something like this. I hope you can visualize. Now, for that big cube surface, which surface am I talking about? This entire surface, this entire big surface. The total flux by Gauss's law is Q by epsilon naught, correct? But that entire surface is made of 8 cubes. The entire surface is made of 8 cubes. Do you understand? So through any one cube, like the one over here, through any one cube, it will be 1/8 of the total. So 1/8 of the total means 1 by 8 of Q by epsilon naught. Think of the cube at the center of that big cube. 1/8 is going here, 1/8 is going there, 1/8 is going here. So 8 cubes it is getting distributed. So hence the answer is A. Perfect. Very good. Very good. How do you use F cos theta in the first question? Vani is asking. Okay. So vector resolution. Were you there in 11th standard? That's it. So you have the force over here, and this is theta. So what is this? This is F cos theta, and this is F sin theta, right? So in this question over here, if this was F1, and let's say I want to bisect, this is 30 degrees. So how much will this be? How much will this be? This will be F1 cos 30, and obviously F1 sin 30 will be over here. That's standard, right? That's how it will be. This will be perpendicular. Makes sense? Got it? Chalo, let's get moving to the next one. Yes, option A is correct. Next, what is the flux from each phase? Now that will be a tricky one. So if you want to calculate it from each phase, then you divide it by 3, because each of those cubes will have 3 phases through which the flux will be flowing, correct? So it will be then Q by 24 epsilon naught. Okay, now many of you are saying B, some of you are saying A. Clearly students are confused. All right, so let's visualize the diagram. First of all, two infinite plane parallel sheets separated by some distance, okay, have equal and opposite uniform charge densities. So if this is positive, okay, then this is negative. Okay, so because of positive, the field lines will look like this. Because of positive, the field lines will look like this. And because of negative, it will be attractive. So it will end over here. It will end over here like this. This is how the field lines will look like. The field at a point between the sheets. That means you are somewhere over here at this point. I think I know what to do. The fields will add. So the field over there will be the field due to the positive charge, also plus the field due to the negative charge. Why? Look at the arrow marks. Positive field is also that right side, negative field is also right side. So they are going to add, they are not going to subtract. That's the common mistake, and many students mark 0 and they get a 0 mark over there as well. So field due to any one sheet, what is it? Sigma by 2 epsilon naught. This is also sigma by 2 epsilon naught. This is plus. So 2 by 2 sigma by epsilon naught. So this is nothing but sigma by epsilon naught. That is option B. Option B. Very good. Very good. Got it? Excellent. So that's how. Oh, by the way, this is also a capacitor. At the end of the day, this is nothing but a capacitor. Cool. Let's get moving to the next one. Sigma by epsilon naught is correct. Moving ahead to the next one. How do you know there are 8 cubes? Shrishta? Okay, meanwhile you guys solve this. Think simply, there was 1 cube over here. Obviously, you can add 1 more cube here. You can add 1 more cube here. And you can add 1 more cube here. So how many cubes are there here? Totally 4 cubes are there. Same thing, you can do it below. So 4 cubes are there. So 4 on the top, 4 below. How many cubes? 8 cubes, right? Makes sense? So 4 on the top, 4 below, and your charge is at the center. That's the reason for that. All right. I hope that makes sense. Okay, many of you are already marking D. Okay, electric dipole with moment of this much is aligned at 30 degrees with the direction of the field. Okay, the magnitude of the torque on the dipole. So what do we do? So the torque will be P E sine theta. Okay, that's the formula for torque. So we are using the torque formula here for dipole. So dipole moment is already given. So 2 into 10 to the power minus 9. Electric field is already given. 4 into 10 to the power 4. Sine theta. So sine of 30 degrees. So let's do this. 2 4s are 8. And we have 10 to the power minus 9 into 10 to the power 4. Sine 30 is half. So 2 goes. This will become 4. Yes, so 4 into 10 to the power minus 5. Just check this out. Option D, everybody is getting it. Very good, very good, very good. Proud of you, my warriors. Let's get moving to the next one. Excellent. I can see that many of you are going to score full marks. Very good. See, CBSE paper is simple. It's at max average. Okay, it's nowhere compared to JEE mains level or even JEE advanced level or even NEET level. So basically, if you are preparing for JEE and preparing for NEET, your term 1 examinations will be this easy, and term 2 will be even more easy because you would have finished the portion much before your term 2 examination. So by the way, even we are having lots of courses even during this time. Even if you are confident that let's say for example you are confident that okay, my term 1 examination is simple, it's going to be easy, and if you think that you want to prepare for term 2 along with JEE, let me tell you, my courses, crash courses are still available, so you can go ahead and check out the links which are there in the description box. So we have these 3 charges and they are placed at the corners of an equilateral triangle. What is the magnitude of the electrical dipole moment? Okay, so Ashutosh, you'll have to wait for some JEE advanced session for very difficult questions, but yes, there are some good questions as well over here. But that is again of CBSE level. I am helpless. Okay, so don't ask me very difficult questions. Okay, we are going to have very difficult questions coming very soon. So this is how the charges are. Oops, sorry, I think I added exactly ulta. This is plus and this is minus. Okay, now once you know these are the charges, here is what I am going to do. This negative 2q, I will just write it as minus q and minus q. Reason is, I know that this plus q and this minus q forms a dipole. This minus q and this plus q also forms another dipole. Each dipole will have its own dipole moment. Let's say I call it P1. This will be also P1. Agreed? This will be P1. This will be also P1. So what is the P1's value? It will be the charge, which is Q, into the length. What is the side length? The side length is given to be L. So it will be Q into L. Don't put it as 2L. It creates confusion. That's why I tell you, don't remember the formula of dipole as charge into 2L. You'll be like, sir, what was L? Was it half? You get confused. So L is just the separation. That's it. Great. Now, the total dipole, the net dipole, will be the vector addition of P1 and this P1. This P1 and this P1. So when you add them vectorially, if you want, you can directly use this formula, which you have studied back in vectors. So it is P1 square plus P1 square plus 2 P1 cos 60. Let's do this. So P1 is common, so P1 just comes outside. 1 plus 2 into cos 60 is half. 2 goes, this becomes 1, so it will become P1 root 3. So P1 is nothing but Q into L into root 3. So Q into L into root 3, which is option C. Very good. Very good. Yes. If it is minus 3Q, then it will not form a dipole. You have to always try to form pairs, equal, positive and negative. Okay, so that's what you are always going to do. So if it is positive, negative over here, you can make a pair here and here. If it is double plus, negative, okay, negative, and let's say another positive over here, you can make one pair here, you can make one pair here and one pair here. So it always has to be equal in number. Keep this in mind. Okay, option C is correct. Moving on to the next one. Okay, why not 2L? Eben, oh my god, see bacha. What is the formula for a dipole moment? It is Q into separation. It is not 2L. That's what is the mistake of, these books. They confuse students. Separation. What is the separation between this charge and this charge? It is L, right? So that's why the separation is L. So when they put the formula in your books, minus and plus, they put this as 2L. Why do you want to confuse? Just remember, it is charge into separation between the charges. Is that clear, bacha? Is that clear? Okay. Why can't you take P1 and P2? Yes, you can take P1 and P2. But why did I take P1 and P1? The reason was, I just knew if this is P1 and if this is P2, magnitude wise, they both are same. Because this is equal amounts of positive and negative. Distance is also same. So magnitude wise both were same. That's why I took it. Else I would have taken it as P1 and P2. What's the harm in that? There's no harm in that. Yes, so Sachin, if you have studied at 2QA, that is something which you should forget. Okay, so that is what many institutes and many teachers fail to explain, and that creates even more confusion. So my method is always remember dipole moment as charge into length, not as 2L. 2L creates confusion. L is the best way to remember because you have the clear clarity that yes, L is just the distance between the positive and the negative charges. The moment you put that 2 there, everything just goes haywire. So don't remember it. Don't remember 2L. That's random. That's wrong. Don't remember it. Okay? It's going to create lots of confusion. Okay? And 60 degree is just, yes, because it's equilateral triangle. Obviously, Kirtana, equilateral triangle 60 degrees. Okay? Mohammed, if you want to learn vectors again, I would advise you to join crash course. So crash course will start right from beginning, right from vectors till the last part. Okay, great. Okay, how do we use F1 cos theta? My god, Suhani, I think I just gave you the answer before that. Okay, 2L use nahi karna hai. 2L use nahi karna hai bachcha, Ibn. 2L is wrong. 2L is don't remember that. Just forget it. 2L करके कुछ चीज था, भूल जाओ उसको. Just remember charge into L. Okay, that's it. Yes. Cool. The value of P1 is not 1. I had taken P1 outside. P1 square was outside. Yes. Okay, P1 square was outside. चलो, मैं थोड़ा अभी slow पढ़ाऊंगा. मेरे को लग रहा है कि you guys are not grasping it so quickly. तो आई एम जस्ट गोइंग टू गो लिटिल बिट स्लो, बिकॉज मेरे को ऐसा लग रहा है कि आप लोग को थोड़ा समझने में थोड़ा स्पीड में दिक्कत हो रहा है. ओके, डोंट वरी, आई विल गो स्लो. एन इनफाइनाइट लाइन चार्ज प्रोड्यूसेस दिस मच फील्ड एट दिस मच डिस्टेंस. फाइंड आउट द फील्ड फाइंड आउट द लीनियर चार्ज डेंसिटी. अच्छा देखो क्या है, we have a line charge like this. Okay, it creates a field around it. Okay, now the question is, find out what is the linear charge density if the field is given. First of all, what is the formula that we know? Field is 1 upon 2 pi epsilon naught lambda by r. That is the standard formula for linear charge density. Okay, now what is the value of field given? 9 into 10 to the power 4. This number over here, I can write it down like this. 2 times of 1 by 4 pi epsilon naught, because this value I know. Lambda, I don't know. R, distance is already given 2 centimeter. Centimeters means 2 into 10 to the power minus 2. Now already many things are getting cancelled, like 2 and 2. Then let's see what else happens over here. Okay, so we have 9 and then this goes over here, so it will become 10 to the power 2 is equal to 1 by 4 pi epsilon naught is 9 into 10 to the power 9 into lambda. So you can again see 9 and 9 gets cancelled, so we just have 10 to the power 2 into 10 to the power minus 9 is equal to lambda. So lambda is 10 to the power minus 7. So 10 to the power minus 7, just check this out. Are you getting it as 10 to the power minus 7? Yep. So it will be how much? D. Yes. There is no shortcut method for linear charge density. Just remember this. So if you want, you can always remember this formula as 2 times of Coulomb's constant into lambda by r. If you want, you can remember it like this. It's one and the same thing. Okay, make it unique. Yep. Very good. Very good. Chalo, let's get moving to the next one coming up. Okay. Very good. Very good. Chalo, let's get moving. Here we have then, oh, by the way, let me also tell you, there is a marathon sessions going on right on our Vedantu platform. So if you are a vPro student, then you can access it for free. But if you want to access it, even if you are outside and you want to access all the chapter wise tests as well as, you know, the discussions that are happening on our platform, you can avail the course which is there in the description box for 899 rupees for physics, chemistry and biology. Okay, so marathon sessions going on right now in our Vedantu platform. Let's move on to electrostatic potential and capacitance quickly, and let's have the formulas out here. Some important formulas which I would like to give you is the relationship between work, potential energy. Okay, so very very important. Work done by any force, or in general we know is integral force dot displacement. But when you talk about work done by conservative force, it is always negative delta U, where this delta U refers to the change in potential energy, meaning final potential energy minus initial potential energy. There is a difference. So for example, you have, let's see whether you can get this. You have a positive charge and you have a negative charge. Okay, now you bring these two charges closer. What do you guys suggest? Has the potential energy over here, and this is the final position. If this was initial potential energy, this is final potential energy, do you think the potential energy has decreased or has it increased? Come on, let me see if you can get this. Has the potential energy increased or has it decreased? P is dipole. It has decreased. Yep, it has in fact decreased. Potential energy has decreased. Now if I ask you what is the force? Well, the force is attractive, and is the force doing this force by electrostatic? Electrostatic force is a conservative force. Is the force doing positive work or negative work? The work done by that electric force, is it positive or is it negative? That answer will be positive, because the force and the displacements are in the same direction. Okay, because force and the displacements are in the same direction, correct? Now if you look at this formula, work done by that force is negative delta U. If you notice, the energy has decreased. So if I ask you what is delta U will be negative because energy has decreased. So hence, work and change in energy will always be of opposite signs. That's what you need to keep in mind. Work done by that internal conservative force will be always negative of the change in potential energy. Remember this. Alright, moving ahead to the next one. Yep. So the next one that you have is, I'm going to give you a beautiful chart for remembering force, potential energy and all these things. So look at this. If you have force, you can go to field, you can also go to energy, you can also go to potential. How do you define force? Force, everybody knows it is K Q1 Q2 or K QQ by R square. Field is nothing but K Q by R square. Potential energy is K Q Q by R. Potential is just K Q by R. You can see one alphabet continues to be stripped away. It goes off for each and every formula. Now, when you want to go from force to field, you basically use this limit. Limit force by charge, Q tends to 0. Same way, when you want to go from energy to potential, limit potential energy per unit charge, Q tends to 0, gives you potential. Energy per unit charge is called potential. Same way, if you go back, okay, like this, then from field, if you want to find force, so force will be charge into field. We know this formula. Same way, from potential you want to go to energy, so the potential energy will be charge into the potential. But this is a scalar equation, there will be no vector. Very good. Hello Logesh, welcome. Yep. So the chat is continuous even. Okay. Next, from force, if you want to go to potential energy, there is an interesting way. So force and potential energy, how are they related with each other? F is minus du by dr. Keep this in mind. Force is minus du by dr. Same way, field and potential are also related with each other. Electric field is minus dv by dr. What is this dv by dr called? dv by dr is also called as potential gradient. Potential gradient. It also means one thing. If you have electric field lines, the electric field lines always go from high voltage or high potential to low voltage, and they are always perpendicular to the equipotential lines. That's what this statement means. Perfect. So this chart helps you remember all the formulas in one go. You can see this. You can go from any place to any place in a very easy manner. Force to field, potential to potential energy, force to potential energy, potential to field. It's all the same thing. Remember, this side is all everything like force or energy per unit charge. So you get field and potential per unit charge. That's all it is. Okay, cool. So these are the formulas that you need to keep in mind. Now, what is the difference between energy and potential? See, whenever you have 3 or 4 charges, let's say 1, 2, 3, 4, each pair of charge will have energy between them. Like the potential energy between 1 and 2 will be K Q1 Q2 divided by R. Similarly between 2 and 4, similarly between 1 and 3, similarly between 3 and 4, similarly between 1 and 4, similarly between 2 and 3. You will have all these terms. So if somebody asks you energy of that particular system, then it will be all those terms added together. It's the total energy of that system. But when somebody asks you potential, it's not of the system, but in fact it is the potential at a point. So if somebody asks you what is the potential at, let's say, some point over here P, then it is potential due to charge 1, potential due to charge 2, potential due to charge 3, potential due to charge 4. So it will be just V1 plus V2 plus V3 plus V4. That's it. So potential due to each charge, you just have to add it as a scalar. That's it. Because potential, remember, is a scalar quantity. Potential just refers to ability, or ability for a charge to create potential energy, or basically it is the work done per unit test charge to bring it from infinity to that particular point. Okay, that's what it is. Perfect. So understand the difference between energy. Energy is of a system. Potential is at a point. It's not yet there. Energy is not yet there. It just has the ability. When you place the charge, then it is going to get the energy. Fair enough. Next, let's go ahead to the next one. So potential formula for a dipole. So standard. So if you again have a dipole, again I am repeating this. If you have negative charge, positive charge, dipole, this is length L. The dipole moment is Q into L, not 2L. Understand? It's the same thing, guys. If you have a negative charge, positive charge, and if I call this as 2A, then I can also call dipole moment as Q into 2A. Here, basically 2A is equal to L. It's one and the same thing. There is no difference, but this is not preferred, this is preferred. This is there in your books, but you're not going to remember this. In fact, you're going to remember this. That is going to make your job easy. But if you want to fall in the pit, then I'm nobody to stop it. So please go and fall if you are not convinced with this method. Alright, next, the thing is, if you find the potential at any point, if you want to find the potential at any point at a distance r, then that is just given by K, which is your Coulomb's constant, standard 9 into 10 to the power 9 into P, Kp, and then you have cos theta divided by r square. One thing that you should keep in mind, okay, so Logesh, this class is for at least 2-3 hours. This is at least for 2-3 hours. This is r square. Usually due to a point charge, when you have potential, you have Kq by r. This r is there. Why is there r square here? Reason is this P has the dimensions of length. Because this has the dimensions of length, so you have to increase the dimension in the denominator. So that's how you can keep in mind it is r square. Remember, for field it was r cube. This is a common mistake which students make. Okay, I hope this is clear. Okay, so when you move from a charge from high potential to low potential, will the energy increase or decrease? Simple. So very interesting question somebody has asked. So if this is low potential, this is high potential, and let's say you take a charge from here to here. It depends whether it is positive or negative. So for negative it will be different, and for positive it will be different. So if you take a positive charge it will be different, and for negative it will be different. Let's see what it will be. So from low to high. So when you take a positive charge from low to high and potential, obviously the energy will increase. But if you take a negative charge, then that energy will decrease. Is that okay? Perfect, perfect, perfect. Great. Chalo. Let's get going ahead. I hope you can understand this point still here. Capacitor formulas. Let's have a look at the formulas in capacitor. So first formula, Q is equal to CV. What is C? C is basically your capacitance. What does this stand for? If you have two conductors, one is positive, one is negative, then there is field between them. There is energy stored between these two conductors which are having a potential difference of V. So one conductor stores plus Q charge, other conductor stores minus Q charge. This charge is related to the voltage with this formula. The amount which it can store on each one is being defined by that capacitance. So capacitance tells you how much charge it can store per unit voltage. Next, how much energy it stores is nothing but half CV square, which is also half Q square by C, or which is also half Q into V. One and the same thing, there is no difference. Perfect, perfect. So Sushma, what do you mean by if you take a dipole? Okay. So what's the difference between Kp cos theta, r square and field? So I think I mentioned it before already. So when you have field, there is a term of root 3 cos square theta plus 1. When it is potential, it is just cos theta. And in case of field, there is r cube, and in case of potential, there is r square. Everything else is same. So this is Kp, this is also Kp. Everything else is same. Okay. I hope that makes sense. This is what it is for a dipole. Alright, moving ahead. Now, the next thing, capacitance for parallel plate. Capacitance for parallel plate capacitor is epsilon naught A by D. epsilon naught A by D. But if you add any medium, then the capacitance becomes K times as compared to when there is nothing inside it. This K is not your 9 to 10 to the power 9. This is called as your dielectric constant. This is called as your dielectric constant. Keep this in mind. Very good. Excellent. Next thing, energy per unit volume. What is energy per unit volume called? It is called as energy density. It is called as energy density. So any field stores energy. How much energy it stores per unit volume is called as energy density. It is given by half epsilon naught E square. So whenever you have field, okay, if you take 1 unit volume out of it, how much energy is there in that field between the capacitor plates or anything in general? Half epsilon naught E square. Perfect. Now the next thing I want you to focus on is also capacitors combination. So say for example, okay, they are in series, very important. So like this, understand each of them will have the same charge, and this is C1, C2, C3, then 1 by C effective is just 1 by C1 plus 1 by C2 plus 1 by C3. So it's exactly reverse to that of resistors. And also remember one thing, the charges are same but the voltages are different. V1, V2, V3. For example, if you want to find V3, use this. It will be Q by C3 because Q is CV. So V will be Q by C for any particular voltage. So it will be Q by C1. Similarly, when it is in parallel, when you have capacitors in parallel, so like this, okay, you have capacitors like this in parallel. This is C1, this is C2, this is C3. In this case, what will be different is the charge. This will be Q1, this will be Q2, this will be Q3. What will be same? Voltage will be same. So you will see voltage is basically same throughout, and C effective will be C1 plus C2 plus C3. Okay, so that's the difference. And if somebody wants to find Q3, Q3 is C3 into V. Q1 is C1 into V. Just use Q is equal to CV formula. That's it. Okay, is that clear? Very good. So Sushma, if you take dipole from high to low potential, well, let me tell you, nothing will happen because see, when you are not changing the orientation and you are taking it in a uniform field, then the work done on the positive charge and the negative charge will be same. So the net work done will be 0 if you are not changing the orientation. The energy changes in a dipole only when you change the orientation. So keep that in mind. Okay, only when you change the orientation. Perfect. Now force between the plates and all of that is not there. It's there for JEE mains. For CBSE point of view, it is not there. So if you are obviously preparing for JEE, then you will find a lot of things missing in CBSE. You will not find so many complicated formulas because so many things are deleted or not there for board's perspective. Okay, so don't worry about it. Great. So let's do some questions based on this. Ready? Sir, even if you decrease or increase the potential, capacitance is constant? Yes, because it only depends on the material and the shape and the size, nothing else. Alright, come on, let's see if we can do this question. Okay, yep, there we have our first question. Come on, let's see. The potential at a point due to the charge is how much? Come on, this is easy one. Come on. Let's do this. Potential at any point, okay, we know is given by K Q by R, and this K is 9 into 10 to the power 9, charge is 5 into 10 to the power minus 7, and distance is 10 centimeter, meaning 0.1 meter. So 9 5s are 45, I think. Yep, yeah, correct. So there we go, into 10 to the power 9, 0.1 goes up 10 to the power 10 and 1 and 10 to the power minus 7. So this will be 45 into 10 to the power 3. So just check this out. 45 into 10 to the power 3 is 4.5 into 10 to the power 4. So option C, perfect. Option C is correct. You can see that. Option C is correct. So 4.5 into 10 to the power 4. That's what it will happen. Perfect. Let's get going to the next one. Moving ahead, 4 equal charges are placed at 4 corners of a square of side A each. Work done in carrying a charge from minus q, from its center to infinity. Now this is going to take some time. Let's see how many of you can do it. In capacitance with series, obviously it is opposite of that of resistors. So for series, use parallel formula for resistors, and for parallel capacitance, use series formulas. Whatever you use for resistance, it's exactly opposite. Okay, moving ahead. Now the answer is definitely not what you guys are thinking it to be. Okay, well. All of you are saying A, sure, paka. Wow, very good, excellent. Some of you are getting a wrong answer. The correct answer is different. Look at this, you guys are getting it wrong. Option B, be careful. Why is it option B? I'll show you. See, you guys got it wrong. Where are the 4 charges? The 4 charges are here on the vertices of the square. So these are the 4 charges. Now you take a charge minus q. Minus q is over here. And you take it from here till infinity. Okay, we know one thing, at infinity energy is 0. So the question is, what is the work done? The work done by external force, remember, is exactly opposite of the work done by the internal conservative forces. So whatever work you do will be utilized, okay, by the internal forces. So if you don't understand this, it's okay. Remember, that whatever work you do goes in changing the energy of the system. It goes directly in changing the energy of the system, which will be final energy minus initial energy. The final energy means energy at infinity. Basically this is infinity. So at infinity the energy is 0. Initial energy is something which you need to calculate. Okay, now look at this. Here you need to find out how much energy did this charge have with respect to this and this. For that you need to know how much is this distance. Now we all know in a square the diagonal, if this is A, this diagonal is root 2 times of A. So this part will be half of root 2a, which is just a by root 2. Correct? This is just half of that diagonal. I will need that because I need how much distance is the charge away from any of the corners. So initial energy, how do you calculate? There will be 4 terms. Energy with this, energy with this, energy with this, energy with this. So 4 terms will be there. So 4 into energy from each corner, energy from each basically corner. So what will it be? Let's try to calculate this. K, Q1, Q2 by R. K is K, Q1 is Q, Q2 is minus Q divided by R. R is nothing but A by root 2. So minus and minus cancels, so it will become 4k q square, and this root 2 is also there. Okay, root 2 divided by a. Now k value you can put, so 4 root 2, 1 by 4 pi epsilon naught, and you have q square by a. This 4 and this 4 cancels, so root 2 q square by pi epsilon naught a. So hence option B is correct. Got it? Very good. So magnetism chapter, yes, cyclotron is deleted. Thank you, Litish. Perfect. Understood, guys? So that's all it is. It's a very common silly mistake. Many students think it is 0. I don't know why you guys think of it as 0. It is not 0. This charge with this had energy. When you shoot it away, the energy disappeared. At infinity it became 0. So the work done was change in the energy. So just use the formula of electrostatic energy. We have applied it directly. Okay, perfect. So next question. The work required to put the 4 charges together at the corners of a square of side A is how much? Let's see how many of you can do this question. The work required to put all the charges at the corner of a square. So you have to assemble it. This is also a kind of question which comes. Ln, Ln, OTR, final energy is 0 because of yesterday's session. I mentioned it. You assume the energy when infinite separation is there is 0. That is your reference energy. So even if you put the formula KQ by R, when R is very large, energy will become 0. So that's how it is 0. Okay. Chalo, let's see how many of you can do this. Many of you are confused between A and C. Okay. A and C. Okay. Sure. A is the guess. Well, the answer is B. I'll tell you how to do this problem. Okay. See, what you need to do is find energy between 1, 2, 2, 3, 3, 4, 4, 1, 1, 3 and 2, 1. All the combinations. So the total work done is basically nothing but the energy of that particular system. Okay. Now let's just calculate this. What is that energy of that system? Okay, let's just calculate that potential energy of that particular system. It will be U12 plus U23 plus U34 plus U41 plus U13 plus U24. So many terms are there. U12 will be, think about it, it will be K, Q1 and Q2. Both are opposite. So Q into Q, which will be minus Q, divided by distance, which is A. Okay, side length is A. Similarly, U23 will be negative positive. So again it will become, K, Q minus Q divided by A. So like that there will be totally 4 terms together. 4 terms. 1, 2, 3 and 4. Till this 4, 1. Each time the charges are opposite, you can see that. The last 2 terms, Q, Q, minus, minus. Minus into minus is also plus. Keep that in mind. So for 1 into 3, what will be your potential energy? Think. So it will be K, Q into Q divided by this distance, which is root 2A. That's the length of the diagonal of a square. Everybody knows this. So root 2A and plus K into minus Q into minus Q. It is anyways going to be positive divided by A. Now you can see everywhere K, Q square by A is constant. It's common. So K, Q square by A is common. Here you get minus 1, here you get minus 1, here you get minus 1, here you get minus 1. 4 times. Here you get plus 1 by root 2 and here you get plus 1 by root 2. Basically this will become K, Q square by A. Here you will get, minus 4 plus 2 by root 2, which is just root 2. Just calculate this, you will get the answer. Just calculate this. Just calculate this. Oh, sorry. Here I had to put root 2A. Yep. So that's it. Just calculate this. You will get the answer. As simple as that. Got it? Perfect. Understood? So it's actually not lengthy. If you are used to solving these questions, this is a standard question which is done. Even in my regular Pathfinder series, when I have completed this chapter, I have done these kind of questions. So you already know this. It's just a matter of calculation. And you should immediately think, Acha, K, Q, Q will be common everywhere. You should not even do this step. You should not even do this step. Your first step should be this. How many of you can start from here? Raise your hand. How many of you can start it right from here? Think. Okay. So let's see. Yeah, very good. Very good. Very good. Some of you are able to solve this. Very good. So if you are able to, so if you are able to solve right from here, that's very good. So you will save a lot of time writing all these steps. Perfect. Now, okay, this is done. Let's get moving ahead to the next question. The charge on the 3 microfarad capacitor is, come on, let's see how many of you can do this. The charge on the 3 microfarad capacitor shown in the figure is how much? Let's see if you can do this really quick. First, what do you need to find? These are 3 capacitors on the series. That means all of them have the same charge. All of them will have same charge. That's understood. Okay. Can we write this as one single capacitor with that same charge? Okay. What will this C be equal to? I think I can find it out like this. 1 by C is equal to 1 by 2 plus 1 by 6 plus 1 by 1 by 3 plus 1 by 6. LCM will be 6. So this will be 3, this will be 2, this will be 1, whole thing divided by 6. 3 plus 2 plus 1 is 6, 6 by 6, which is 1 by 1. So capacitance is 1 microfarad. Okay, so capacitance is 1 microfarad, we got it. So what is the charge on this? The charge will be C into V. C is 1 micro, okay, into voltage. Voltage is 10, so it will be 10 microcoulombs. So answer is 10 microcoulombs. That's it, done. Okay, yes, the only extra preparation JEE students need is just practice of those kind of questions within the time. Your speed matters and that knowledge of NCERT matters. So that's the only extra preparation you need to do. Perfect, because JEE problems are slightly more on the conceptual side and more on the analytical skill sides and all of that. Okay, so we have a parallel plate capacitor of capacitance C. Half of it is filled with constant K, dielectric material. How much is the percentage change in the capacitance? Beautiful question. Okay, so yes, you're going to get break after some time. Yep, hold on. So after one more chapter maybe. Current electricity. So what do we need to do over here? Think. This capacitor can be divided into two parts. The upper part and the lower part. Upper part is having air, lower part is having the dielectric material. So I can write it like this. Just write it like this. Okay, just think about it. Yep. Two capacitors in parallel, one of them has dielectric, the other one does not have dielectric. Correct? Okay. Now we know what happens when capacitors are in parallel. They just add. Okay, the equivalent capacitance just will be the addition of them. What will be the capacitance of this part? And what will be the capacitance of this part before I add it? So for that, think this way. If the original area was A, if the original area of the plates was A, this plate will have area A by 2, this plate will have area A by 2. So this capacitance will be epsilon naught A by 2 by D. This capacitor will have a capacitance of epsilon naught but dielectric constant, which is 5. So into 5 into A by 2 by D. Perfect? Okay. So the total effective capacitance will be just C1 plus C2 because they are in parallel. Keep this in mind. You just add them. So that plus that. So epsilon naught A by 2D is there. This is the first term, but the second term just has 5. So this will become just 6 in the next step. So epsilon naught A by 2D, 1 plus 5, 1 plus 5 is just 6. So this 2 and this 6 goes, this will become 3. So 3 epsilon naught A by D. 3 epsilon naught A by D. So epsilon naught A by D is the capacitance initial. So what is this C effective? This C effective is giving me the new capacitance. So earlier it was C, now it has become 3C. How much is the change? How much is the change? Is it 200%? Is it 400%? What do you guys say? Is it B? Think again. Be careful. I don't know why you guys are saying B. Is it B option? Think again. How is it B? Earlier it was 100. Now it has become 300. So how much is the percentage change? How much is the percentage change? Be careful. 33%? What are you guys saying? How is it 33%? How is it 33%? It is D. What are you guys saying? It was 100 for example. Now it becomes 3 times of that. It becomes 300. What's the percentage increase? How much is the increase? The increase will be 2C. 2C means twice. 200% increase. Guys, be careful about this. Many of you made a mistake over here. You had 100 laddus. Now you have 300 laddus. How much is the increase? The increase is 200 laddus. So how much is the percentage increase? Think about it. Okay, so it's 200%. Yep, be careful. Many of you made that mistake. 16 picofarad capacitor is connected to 80 volt supply. The amount of energy stored in it is how much? Come on, let's do this. Simple direct application based questions. These kind of questions are going to come in the examination. Direct application. Yeah, why not possible? क्यों नहीं possible है? 200%. So when you add dielectric, Rahul, what happens? Capacitance increases that many times. If the constant is 2, it becomes 2 times. So if capacitance becomes 2 times, obviously everything else in it also starts changing accordingly. Understand that. Okay, so amount of energy stored is nothing but half. Which formula will I use? capacitance is given, voltage is given. So half CV square. So capacitance is 16 pico. Pico is 10 to the power minus 12 into voltage, which is 80 square. So this will become just 8. So 8 into 10 to the power minus 12 into, I'll write this as 8 square into 10 raised to 2. 8 cube. 8 cube is 512. This will become into 10 to the power minus 10. So I think this will be the answer. Just check this out. This will be the answer. 5.12 into 10 to the power minus 8. Okay, you can just shift the decimals. 5.12 into 10 to the power minus 8. You can just take the two decimals inside. Yep, perfect, very good, excellent. Moving ahead to the next one. Okay, current electricity. All right, it can decrease, Ashutosh, only if the dielectric is removed. Okay, not before that. Okay, there are very few formulas here, and then let's straight away go to some questions. Okay, let's get going. Ready? Uncharted, the work done minus of U, so shouldn't it be C? I think you're referring to some previous question. If it was work done which was asked, work done is final minus initial. You are saying for the previous one. Which one? This one somewhere here. Oh, this one. The work required to put the four charges together. I think we got the answer as negative. Yes. If it is the work done which is asked, yep. If it was the work done which is asked, the work done will be final minus initial potential energy. Now let's see, the final answer in this situation was negative. Initial was 0 because initial means it was at infinity. So the final answer will be negative. So it is correct only, bacha. It is correct. It is fine. Uncharted, it is fine. Perfectly fine. Final itself is negative. We got the answer of energy itself as negative. So it comes out to be negative. Is that okay? Sarvana, if you keep solving problems now, it becomes easy. And another easy way to remember energy stored in a capacitor is, remember energy stored in a spring is half kx square. So if you remember this, you can get this also. I'll tell you why. X is similar to charge and spring constant is similar to 1 by c. So if you remember that, you will get this. K is similar to 1 by c and x is similar to charge. So half q square by c. Half q square by c. One and the same thing. There are direct relationships. Yes. No, final is not infinity. You are bringing the charges together. Read the question. Required to put the four charges together. So what is final? Final is what is given. Initial will be, they are very far away. So that's why, understand, initial is 0. Understood? Got it? Final is not infinity. Read the question. Work done to put them together. That means what? The charges were very, very far away. Now you brought them from infinity very close to each other. So final is not 0. Be careful. Yeah, common mistake. Common mistake. Very good. Very good. Yeah. All right. Understood. Perfect. Great. Let's move on. Okay. So this work is done by the external force. Okay. So this common misconception is there between many students. Sir, I never understand. Work is delta U or work is minus delta U. Let me tell you the difference. Work done by external force is plus delta U. Work done by that internal conservative forces is, okay, so that basically that conservative forces is negative delta U. So this is the actual relationship. And here what has been asked is the work done externally, not internal. Be careful about it. Cool? Chalo. Perfect. Understood? Let's get going. All right. Are you now ready? Convinced? Perfect. Everything done?